Good morning, students. Welcome to Commutative Algebra lectures. In this lecture, we'll discuss about Noetherian and Artinian modules. Okay, so let's start with some basic definitions and results. So consider sigma with a relation which is opposite. Okay, then we can have the two conditions which are equivalent, namely every increasing sequence. Say suppose you take x1 less than or equal to x2 and so on in sigma. This, if it is stationary, this is stationary. What is meant by saying stationary? There is some n such that xn is same as xn plus 1, xn plus 2 and so on. That means after some stage all elements are equal. This one is same as saying that every non-empty subset of sigma has a maximal element. So if you take any S which is non-empty subset of sigma, then this S has a maximal, okay, element. Right? This is one and this is two. These two are equivalent, and proof is not at all difficult. If at all you want to say proof, suppose one implies two, right? You assume that every sequence, okay, is stationary, then increasing sequence. If you have an increasing sequence, then it is stationary is given to us. We want to show that if you take any non-empty subset of sigma, then it has a maximal element. Okay, so start with, say suppose t. Okay, and assume that it is a non-empty but it has no maximal element. Then we should get contradiction to the first assumption. Okay, so what is meant saying that it has no maximal element? That means given any xn in t, there exists xn plus 1, okay, xn plus 1 in t such that xn is strictly less than xn plus 1. That means given, if you give any element, I can find another element which is strictly bigger than this, right? That shows that you have x1, x2 and so on. Okay, if necessary you can rename them. So you are getting a sequence which is strictly increasing and not a stationary one, right? So that gives a contradiction to that every increasing sequence is stationary. That arises because we have assumed that it has no maximal element. Therefore every non-empty subset of sigma should have a maximal element. 2 implies 1 is again similar. We want to show that if you take any increasing sequence, then it should be stationary. Okay, so if you consider, say suppose x1 x2, you consider an increasing sequence, we want to show that it should stop, I mean it is equal after some stage, all elements are equal. Simply if you take this one, this x m greater than or equal to 1, if you consider this set, then clearly it is a non-empty subset, right? And by second assumption, this should have a maximal element, right? So you can call it, say suppose xn is maximal element. What is meant by saying that it is maximal? That means every element is less than or equal to this for every m greater than or equal to 1. Okay, so in particular if you take n plus 1 and so on, that means if you take m is equal to n plus 1, then what you get is n plus 1 is less than or equal to xn, but we know xn is an increase in sequence, so it is xn plus 1. That shows that xn is equal to xn plus 1. And not only this, if you take n plus 2, n plus 3 and so on, so it is true for all I greater than or equal to 1. That shows that this is a stationary, right? Why we require these two conditions? Based on these two conditions, now we define what is meant by Noetherian module as well as Artinian module. For that, now you take this sigma. Okay, you take this sigma, which is instead of taking any poset, you take the elements are set of submodules, okay, of m, where m is a module, a is a ring, m is an a module. Then consider this as set of all submodules, and this is nothing but simply inclusion. Okay, that means m1 is less than or equal to m2 if m1 is contained in m. Okay, so with respect to this, you have this, you can call it here. Okay, this is inclusion. right? Then the above condition, whatever with respect to this condition 1, okay, increasing sequence, whatever we call it here, this is called as ascending chain condition. So with respect to this, whatever the one above increasing sequence, that one is called ACC, if you can call it ascending chain condition, and the second one is called maximal condition. Okay, second one is called maximal condition. And if you consider instead of this one, if you consider this, okay, superset, okay, then whatever that one is called DCC, decreasing chain condition, and second one is called minimal condition. Okay, minimal condition. Now we can define with respect to these two module M. So you can define what is meant by Noetherian module. So a module M is said to be Noetherian. M is Noetherian or ring A if it satisfies any one of these two conditions. That means ACC are maximal condition. Okay, if M satisfies ACC are maximal condition. Okay, and you will say that M is Artinian if M satisfies DCC are minimal condition. Okay, so what is meaning of saying that ACC? If you have a increasing sequence of submodules, then it should be stationary. And if you maximal condition means if every non-empty subset of submodules M has a maximal element. Okay, fine. Now let's see some properties of this Noetherian module, and most of the places those properties are also applied for Artinian modules. Okay, let's see quickly some examples of if you take G, which is a finite abelian group, okay, finite abelian group, then we know that G is a Z module. Okay, so G is a Z module, and what are all submodules here? So submodules are nothing but subgroups, right? But once G is a finite abelian group, then we know that because once it has a finite group, then the only possible subgroups are finite again, right? So you will have only finitely many subgroups. So therefore, as G has finitely many subgroups, what we can see is that if you take any increasing sequence of submodules or decreasing sequence of submodules, they should be stationary after some stage. That shows that this G is both Noetherian, okay, as well as Artinian. Okay, so a finite abelian group is both Noetherian as well as Artinian module. Okay, Z module. Fine. You take the second example. The second example is Z. So Z is Noetherian, okay, but not Artinian. That means it satisfies ACC but not DCC. Okay, satisfying ACC is not at all difficult, but what we should observe is here that what are the submodules when you consider Z. Okay, so what are the submodules? Are precisely ideals. In particular, they are all principal ideals. In Z, we have principal ideals, right? Okay, so if you can observe that this N is a sub module of M if and only if M should divide N. Okay, right? So it is not N divide M, it is M divide N, that you can easily check, right? So therefore, using this one, if you have a sequence of ideals, increasing sequence of ideals, then you see that this N2, okay, should be a divisor of N1. Similarly, N3 is a divisor of, so you can start considering this, okay, and then this, Similarly here, all if you start considering, then what we can observe here is that each ni, okay, each ni is a each ni is a divisor of n1, okay. But any, we know that if you take any positive integer, it will have only finitely many divisors, positive divisors. So therefore this ni should be finitely many numbers. That shows that it should stop, right? Okay, after that they are all equal, right? That shows that this increasing sequence is stationary and hence Z satisfies ACC condition, so it is Noetherian, right? But it is not Artinian, or it doesn't satisfy DCC. This is very clear. If you take any A which is non-zero element, then you take their multiples A square, A cube, and so on, then it is strictly decreasing, okay, and so on. So which is not going to stop. So therefore, it is not Artinian, right? Okay. Now let's see some other examples. Okay. So we can prove that the result for submodules M is Noetherian. Okay, so this result is mainly true for Noetherian, not true for Artinian. Okay, so what this theorem says is that this M is Noetherian, of course, as a module, Noetherian module, if and only if every submodule. Okay, so if you take n subset of M, which is a submodule, is finitely generated a module. Okay, so for example, what we can understand here is that if we want to show something is Noetherian, if we can show that every submodule is finitely generated, then that module is Noetherian. Okay, or if we know that there is some submodule which is not finitely generated, then we can say that it is not a Noetherian. Okay, and so on. Proof is not at all difficult one. Suppose assume that M is Noetherian, then we want to show that every submodule is finitely generated. So consider N a submodule of M, and then you consider sigma set of all finitely generated submodules of N. Okay. So what is our sigma? Sigma is set of all finitely generated submodules. So N prime is finitely generated, okay, submodule of N. Then this uh, this one, sorry, these are all finitely submodules of, sorry, submodules of not M, submodules of M. Let sigma be the set of all finitely generated submodules of M, right? Then this is non-empty because we know 0 is a submodule of M, which is non-empty and finitely generated, and as M is given to be Noetherian, so therefore this has a maximal element, we can call it N naught. Okay, so we can call it N naught, which is maximum, and that is finitely generated, and we'll show that this N naught, okay, is equal to M. So suppose if N naught is strictly contained in N, then mm, sorry, here actually you take here you take these are all submodules of N only. Okay, then if N naught is strictly contained in N, then there exists X belongs to N such that X is not in N naught. Okay, so X is not in N naught. This implies we know already N naught is finitely generated, and by adding one more element N naught plus X, this is again a finitely generated module, and it strictly contains N naught. This is a contradiction to maximality of N naught. Therefore that arises because we have assumed that N naught is not equal to N, so that means N naught should be equal to N, implies N is also finitely generated. Okay, so we prove that if M is Noetherian, then every submodule of that is finitely generated. Conversely, assume that every submodule of M is finitely generated. Then we want to show that M is Noetherian. To do that, you take M1, M2, and so on is an increasing sequence of submodules. Okay, increasing sequence of submodules. Then we know that if you consider N as union of MIs, okay, this is also again a submodule. But by assumption, we know that this N is finitely generated, right? Say suppose assume it is generated by x1, x2, some xr. Okay, N is generated by these things. because xi belongs to n and n is this. So what we know is that each xi belongs to some m ni for some I. Okay, I is from 1 to up to r, right? Now because it is increasing 1, if you take maximum of these ni's, then all xi's belongs to there. So that is the idea. So therefore if you consider n, okay, n which is maximum of these ni's, n1 n2 up to nr, then xi belongs to mn for every I, because mn1 is containing mn, mn2 is containing mn, and so on, right? So this xi belongs to mn and n is generated by xi. That shows that this uh, m this xi belongs to n and xi also belongs to n. That means this uh, n, because n is generated by xi's and xi's belongs to n, so therefore n is contained in mn, but mn is contained in n because n is nothing but union of mi's, right? So in particular mn is also there. That shows that n is equal to mn. So if n is equal to mn, then the mn plus 1 you take, suppose mn plus 1, okay, is contained in this n, but n is contained in mn. So that shows that this n is equal to mn, which we know. So therefore mn plus 1, okay, mn plus 1 is contained in union of mi. I is equal to 1 to infinity, which is we know already same as n. Here we have already did that, right? But this n is nothing but mn, right? But mn we know is increasing, is contained in mn plus 1. So if you combine these two, what we get here is that mn is same as mn plus 1, which is same as mn plus 2, and so on. So therefore this is a stationary, hence our given module m is Noetherian. Okay. Fine. Now let's talk about next one, which is in terms of exact sequence. So what this result says is that if we have an exact sequence, okay, 0 to m prime to m and m double prime, okay, if this is an exact sequence, we call it this is alpha and beta, then m is Noetherian if and only if m prime and m double prime. M is Noetherian if and only if m prime and m double prime Noetherian. Similarly m is Artinian if and only if m prime and m double prime are Artinian. We'll discuss for Noetherian, same way the same result follows for Artinian also. Okay, fine. How? Suppose assume that m is Noetherian. So if m is proof, suppose assume that m is Noetherian. Okay, then we want to show that m prime and m double prime are Noetherian. So by definition, if we want to prove something is Noetherian, we consider an increasing sequence of submodules of that, and we have to show that sequence is stationary, right? So if you consider this m1 prime, m2 prime, and so on, okay, submodules of m prime, right? But because m prime is a submodule of m, therefore they are also submodules of m prime. That means this will become stationary, as by considering these are submodules of m. Why that is true, where we are using the fact that because this is a 0 to m prime to m double prime is exact. What is meaning of saying that exact? This alpha is injective, okay, and beta is surjective, and image of this alpha is same as kernel of beta. But what is meant by saying alpha is injective? You can consider m prime as a submodule of m, right? And this beta is surjective, means m double prime is isomorphic to m over m prime, okay, because this image is same as this one, kernel, and so on, right? Okay, so using this fact, we can rewrite this statement as m is Noetherian if and only if m prime and m modulo m prime should be Noetherian, right? So that's why we have proved that m prime is Noetherian is very simple by considering increasing chain of submodules of m prime. Okay. Now to show that m modulo m prime is Noetherian, what we have to consider a sequence of increasing sequence of submodules of m modulo m prime, right? How it will be, suppose you call it m1 modulo m prime, m2 modulo m prime, okay, m3 modulo m prime, and so on. Now again, from this, can we get a sequence of submodules of m? Then we can use the fact that m is Noetherian, we get a stationary one. That is clear because m1 modulo m prime is contained here. That means m prime is contained in m1 and m1 is contained in m2, contained in n3, and so on. So we get a sequence of submodules of m now, right? Submodules of m. Now as m is stationary, there exists some k or whatever you can call it, or n. So mn is same as mn plus 1 and so on. So once this is true, then if you go modulo this is also true, right? That shows that m modulo m prime is also Noetherian, right? Now conversely, assume that m prime and m modulo m prime, they are Noetherian, okay? Then we want to show that m is Noetherian, so start with m1 increasing sequence, okay? Somehow we want to show that this is stationary, and what is the idea? The idea is somehow we should get here an increasing sequence, also an increasing sequence here, then use the fact that these are Noetherian, so you get some stationary sequences there and bring it back to here, right? That is the idea. Fine. How we do that? Obviously, when m1 is a submodule of m, then by intersecting m prime you will get a submodule, right? So m prime intersection m1 is a submodule and it is contained here, right? Now they are all submodules of, they are submodules of m prime, okay? Therefore, using the fact that this m prime is Noetherian, what we get is there exists some I such that m prime intersection mi is same as m prime intersection mi plus 1, okay, and so on, right? So there exists some I. Similarly, now how we get uh, this m modulo m prime? So you take m1, okay, then somehow you should go here, so that you take m prime modulo m prime, okay? Then clearly this one is contained in m2 plus m prime modulo m prime, and so on. So we have a now this submodules, so submodules in m uh, m modulo m prime, okay? So again, by using that m modulo m prime is this, so there exists j such that this mj plus m prime modulo m prime is equal to mj plus 1 plus m prime modulo m prime, and so on. Okay. Now, right. So you take, obviously because we want to get it common for both, so you take, suppose call it n, which is maximum of this I comma j. Then whatever we have mentioned here, this is true for, that means this m prime, okay? So this m prime, this will be true. M in mn intersection m prime is equal to mn plus 1 intersection m prime. You can call it, if necessary, it is as k. And it is also true for the second one is also true for n, because n is bigger than I as well as n is bigger than j, right? But we know already, if m1 and m2 are two submodules, then m1 plus m2 upon m2 is isomorphic to m1 upon m1 intersection m2. So instead of using this, now what we do is we use this, okay? So therefore, what is this mn plus m prime modulo m prime? This is isomorphic to mn, right? Mn upon mn intersection m prime, okay? And what is similarly, what is the other one will become? The other one will become mn plus 1. So therefore that other one is mn plus 1 upon mn plus 1 intersection m prime, right? But now you know that, you see from here, this one is same as this, right? So if you call it that as k, so what we got here is mn upon k is actually equal to mn plus 1 upon k, right, as cosets, right? and they are all submodules of, so they are submodules of M modulo K. That shows that this implies this K is contained in Mn plus 1 and Mn plus 1 is contained in Mn, right? This implies, but because it is an increasing sequence, we get that Mn plus 1 is same as Mn, right? That shows that that given sequence is stationary, right? So therefore M is Noetherian. The same way, whatever we have proved here, okay, instead of taking increasing sequence, you try to take decreasing sequence, okay, and apply all these things we get for Artinian, right? Fine. Now, as a simple corollary, if mi's, okay, if mi's are Noetherian, say suppose finitely many, then the direct sum of mi's, okay, is also Noetherian, and the same result is true for Artinian also, okay. Fine. uh, it is very simple. If you have an exact sequence, then we can claim from our result. So how we do that? You take for m1 and m2. See, so first you take m1 direct sum m2, we show that this is Noetherian, okay. So how we show this is Noetherian? Because from m2 to m1 direct sum m2 we have an inclusion map, right? Then from m1 plus direct sum m2 to m1 plus direct sum m2 upon m2, okay, we have a map which is actually isomorphic to m1, then we have map to 0. So this is an exact sequence, right? So if this is an exact sequence, then by previous result, what we can claim is that whenever m1 and m2 they are Noetherian, then m1 plus direct sum m2, this is also Noetherian, right? Then you can prove it. Assume for by mathematical induction, direct sum of mi's, I is equal to 1 to n minus 1. Suppose this is Noetherian, okay. Then we want to show that direct sum of n mi from I is equal to 1 to n is also Noetherian. So you take this and take mn, okay. So apply the whatever case 2. So apply for this one as well as this, you get uh, the required result, okay. So induction is not at all difficult one, right? Fine. Now the other one is, suppose you take A, which is a Noetherian ring. What is meant by saying Noetherian ring? As we know, every ring can be considered as a module. So a Noetherian ring means when it considered as a module. Okay, and M, which is finitely generated a module. Okay, then M is also Noetherian. Okay, so if we know that base ring, whatever, if it is Noetherian and your M is finitely generated, then it is Noetherian, and that result you can apply for Artinian also. Okay, that you can apply for Artinian, right? Proof is not a difficult one; it is very simple. We can again apply for using this above this result, right? Because M is finitely generated. So as M is finitely generated, we know already that M is a quotient of some a power n. That means M is actually isomorphic to a power n by kernel of some map 5, right? Precisely, you can give what is that map from an to m, because M is finitely generated. If you take an, that means n tuple, then we can send it this summation ei xi's, okay, where xi's are nothing but generators for M, right? Under this map you can easily show that M is isomorphic to an upon kernel of phi, right? Therefore uh, we know that because A is given to be Noetherian, therefore a power n, so what is given as A is Noetherian implies this an, which is direct sum of a n times, is also Noetherian. Because what is this an? An is direct sum of a n times, okay. Ai, which is same as a n times, okay. This is also Noetherian by previous result, right? Then we have an exact sequence 0 to kernel of phi to an to this an upon kernel of phi, which is nothing but m, you can call it isomorphic to 0. So this is exact sequence, right? So this is exact, and we know this an is Noetherian, so therefore this kernel of phi and the other one m should be Noetherian. This shows that this m is Noetherian, right? Fine. Similarly, you have another result for in terms of ideals. What it says is that if a is again Noetherian, okay, and a is an ideal of a, then you can consider this a modulo a. This is a will become a ring, and as a module, if you consider this is a Noetherian ring. Okay, right? So how you can prove this? The proof is again using the exactness 0 to the ideal a. Then you have an inclusion map. Then you have a surjective map. Okay, then to 0. This is exact, right? That means as a is Noetherian, what you have here is a modulo e is Noetherian, right? Okay, so the as a considering as a module over Noetherian over this a modulo e, right? So therefore this is a in fact Noetherian ring. Okay, so these are all about Noetherian and as well as Artinian rings properties, and in next class we'll see some more properties of Noetherian modules. Okay, we'll stop here.